Hello, everyone. Welcome to our discussion on PhysioEx number 7. And PhysioEx number 7 deals with respiratory system mechanics. You were asked to do activity 1, activity 2, and activity 3, all 3 activities. It was a pretty short exercise. Let's go over activity 1. And as usual, the items listed here towards the bottom left of the slide are questions and concepts that you should be able to master by the end of performing the experiment and this discussion. So in activity 1, we were measuring respiratory volumes and we were calculating capacities. To remind you from lecture, a respiratory capacity, there are 4 of them, is basically 2 or more respiratory volumes added together. And there are 4 respiratory volumes that you learned from lecture as well. The 4 respiratory volumes are tidal volume, and that's the amount of air that is inhaled and exhaled with every breath. It's typically 500 milliliters. Inspiratory reserve volume, which is the amount of air that can be forcefully inspired after a normal inhale. Expiratory reserve volume, or ERV, is the amount of air that can be exhaled after a normal exhale. So it's the extra air you can blow out. And residual volume, which is the amount of air remaining in your lungs after you have blown out all the air you can forcibly exhale. The 4 capacities are total lung capacity, which is the maximum amount of air in your lungs after a maximum inhale. And TLC equals tidal volume plus inspiratory reserve volume plus expiratory reserve volume and residual volume. Typically, this is about 5 to 6 liters of air, depending on if you're female or male. We're going to go with an average about 5. Vital capacity is the maximum amount of air that can be inspired and expired. So the amount you can go from your maximum inhalation to your maximum exhalation with maximal effort. That's vital capacity. And one way to calculate this is tidal volume plus inspiratory reserve volume plus expiratory reserve volume. Forced vital capacity is the amount of air that can be expelled when the subject takes the deepest possible inhale and then forcibly exhales as completely and rapidly as possible. This is different than a slow vital capacity. In healthy people, the 2 capacities, the volumes of them for slow versus forced vital capacity are typically pretty much the same. But the slow vital capacity and forced vital capacity, as you learned when we did this lab together, at least for our spirometry labs, I should say, can be different in the disease state. Forced expiratory volume 1, FEV1. This measures the percentage of vital capacity that is exhaled in the first second of exhale. So again, our 4 capacities, just to highlight those again, are total lung capacity, vital capacity, and the 2 that I did not go over are functional residual capacity. That's the amount of air remaining in the lungs at the end of a normal exhale. Inspiratory capacity is the amount of air that can be inhaled after a normal exhale. Inspiratory capacity includes tidal volume plus inspiratory reserve volume. Functional residual capacity, to go over it again, includes expiratory reserve volume plus residual volume. let's go over our data now for activity 1. And the data that I want you to pay attention to the most would be the radius. This, of course, is referring to the radius of your air passageways, the flow rate, the flow of air, which is in liters per minute. And I would also like you to pay attention to FEV1 for right now. Notice that breathing rate is kept steady and constant. If we look at our radius column, we see that our first row is our baseline read. That's going to be our baseline read. And then in our second experiment, notice that we are now augmenting our baseline read. We're actually seeing how much air is being able to be inhaled after a normal inhalation, etc. So both the first and second row are basically our baseline reads. Now let's look at the subsequent rows. Notice here, we decrease the radius of air passageways, so they are going down. Notice that airflow is also going down. And also realize that the FEV1 is also going down. And this is because as the radius decreases, we're trapping more dirty air behind the obstructed air passageway. So this is allowing us to compare an obstructive disorder. And we can see that the FEV1 is going down. We also can see that the forced vital capacity, or VC, I should say, is also going down. Obstructive disorders, I'll remind you, are going to be, we're going to see patients with problems with exhale or gas exchange. And again, there's going to be some sort of obstruction in the air passageways. With restrictive disorders, we're going to see that this is a problem with inhalation. All right, moving on to experiment number 2. With experiment number 2, we were looking at comparative spirometry. And we took a lot of data for this activity, and most notably, we were playing with a patient that had emphysema. We had a patient that was experiencing an asthma attack. And then we also looked at a person who was exercising, moderate to heavy exercise. So our data, I'll address the exercise in just a moment, but first I want to start with normal. That's our baseline read. And the rows that I want you to pay attention to the most, I'm going to highlight in blue. I want you to pay attention to FEV1 percent. FEV1% means it's FEV1 divided by FVC. So the FEV1% is our ratio of the amount of air exhaled in the first second versus the total amount of air that is forcibly exhaled, going from a maximum inhale to a maximum exhale. The other column I want you to pay attention to is FEV1 and forced vital capacity. Again, our last column is determined by dividing FEV1 by FVC. When we get to the exercise, I want you to pay attention to the ERV and IRV columns. And then I also want you to pay attention to the tidal volume. Okay. The rest, the other columns, I'm not so much interested in for the purpose of testing. So let's look at our patient that is having an asthma attack. Let's start with that person. He looked like Ed Sheeran to me, red-headed person, and it was kind of creepy that these people blinked as we were taking their information. Notice that this person has a reduced tidal volume. They are having an acute inflammatory response. We remembered that there is an allergen binding to an IgE, binding to a mast cell, which then releases granules that are filled with histamine and heparin. Notice that this person has a reduced FEV1, a reduced FVC, and a very reduced FEV 1%. It is definitely below our 80 percentile mark. After this person has their inhaler, though, and I'll still highlight it in pink, but just a lighter pink, notice that their volumes and capacities are definitely improving. The tidal volume has gone back. Their FEV 1% has gone back to that 80 percentile mark. And their FEV1, which is still a little bit low compared to the normal baseline read, and FVC, again, a little bit low, but they have improved. And the most important part is that the FEV 1% has gone back to that 80% mark. Now let's look at our patient with emphysema, which I will highlight in green. And again, their tidal volume with patients with emphysema, they have a big problem with gas exchange. They have destruction of alveoli, and they also change their breathing rate and depth. So they can take deep inhales and they do very slow exhales. And notice that this person, if we ask them to do a forced expiratory exhale, a forced vital capacity, if you will, that their FEV 1% is again below that 80%. There is no magic inhaler to give a patient with emphysema, that like albuterol, of course, that would improve their condition. So this is a lifelong effect on their FEV 1%. Now let's address the moderate to heavy exercise. Notice that as you start to exercise, your tidal volume goes up. If your tidal volume is going up, let's go back to slide 2. If your tidal volume goes up, and let me highlight that in green, if your tidal volume is now going like this because you're running, notice what happens to the amount of inspiratory reserve volume you have left. It has gone down. Notice what has happened to your expiratory reserve volume. It also has decreased. So reserve volumes, think of that as your savings in your bank account. Your savings is there in case you need it. It is reserve. If you have bigger bills than normal, you're going to tap into your reserves to pay your bills. Well, then what happens to the amount of money in your reserves? It goes down, of course. That's what reserves are for. So notice with the moderate to heavy exercise, the amount of reserves, the volumes for expiratory reserve volume and inspiratory reserve volume are going down as the tidal volume goes up. Moving on to our last activity, we have, in this activity, we're looking at the effect of surfactant. And we're also going to look at intrapleural pressure, these two things, on how they affect respiration. Surfactant, I'll remind you, is a detergent-like molecule that is found within the alveolar space, reducing surface tension from the watery environment, that mucous membrane that we find within our lungs. The intrapleural cavity, or the intrapleural space, is the cavity, this slit-like space that has pleural fluid in it in between the parietal and visceral pleura. Intrapleural pressure should always be negative. It becomes even more negative as you begin to inhale. If we have a pneumothorax or hemothorax, if we have some sort of wound puncturing the chest wall even, it can allow air to enter, and blood, to enter the intrapleural cavity, in which case there is no longer a negative pressure. There is no longer a vacuum. And the lungs will recoil, they will collapse. It's called an atelectasis. And now that means the lungs will no longer be compliant with the chest wall. Inhalation will be very difficult. So first, let's look at our baseline read again. So our baseline read, we have no surfactant. And in our right and left intrapleural cavity, we have a negative pressure, a vacuum. And then in the next set of experiments, we start to increase surfactant. We go from 0 to 2 to 4. And notice that as we have surfactant, our airflow improves. Why? Surfactant lack is a restrictive disorder, making the lungs overly recoiled and less compliant. As we add the surfactant, notice that the lungs become more compliant, they are more distensible, and we see airflow improve dramatically. Then we go back to our baseline read again. Go back to normal, or what our baseline was. And now we are going to create an atelectasis. We are going to allow the intrapleural pressure in around the left lung to become equal to atmospheric pressure. So there is no pressure difference. Notice what happens to the airflow. It's basically cut in half. Why? Because the left lung is no longer compliant. It is recoiled. We're only getting the right lung ventilating well. And then as we, when we plug up the hole, when we seal the wound, that's this row here, where we seal the wound, but we did not restore the negative pressure. Notice that didn't help anything. We still have a total airflow of half of what we started with. It's not until we seal the wound and restore, get a different color here, and restore the negative pressure in the left pleural cavity that our total airflow goes back to normal. Okay, well, thank you for listening to our review of PhysioEx number 7.